Okay, so we will start today's session. So I'm writing down the first question. Okay, I will give you 5 minutes for this. When you're done with the question, put the answer in the comment section. So I would like to clarify that by FPS single precision, the total number of bits will be 32. When it is double precision, the total number of bits will be 64. And when it is revised 14-bit representation, then it will be of 14 bits. So in case of single precision, the size of the exponent will be 8 bits. In case of revised 14-bit representation, the size of the exponent will be 5 bits. So I will discuss the solution now. So this is the expected answer. Um, is there any problem or doubts? Let me know in the comment section. Otherwise, I will move to the next question. Hmm. So I will explain this. So the question you are asking, how did I get the exponent part? So in first of all, if you have any binary number, for example, if this is your binary number, right? So it has to be normalized. There are so it will so by normalization it means yeah. So by normalization it means that it has to be represented in the power of 2. Okay, in this way. So it has shifted by these many bits. So 1, 2, 3, 4, 5, 6. So 2 power 6. Okay. So this part will basically contribute to mantissa, and this part is exponent. Okay. So this I'm particularly explaining for the float point, uh, single this one, single precision float point binary equivalent. Okay. So in this case, this is your mantissa and this is your exponent. Now, uh, in this single precision float point, your exponent bits are 8 bits, right? So for that, we add a bias of 127 to whatever exponent we have. For example, in this case, our exponent is 6. So our exponent in this representation will be 127 plus 6, fine, which will be 133. If suppose if a case appears where the exponent is minus 5, okay, so in that case the exponent in the representation will be 127 minus 5, which will be 122. Okay. Um, so once you have this exponent, you will convert them into equivalent binary representation. Okay, and plug in the exponent part, which is this part. Then you have the mantissa, which you will put after the exponent, and then finally there is sign. Okay, so is this clear to everyone?
Yeah, somewhat.
Okay, if it is clear, I will proceed to the next question. So the next question is this: you have to find the minterms of AB plus ACD, and there are 4 options. I will give you about 5 minutes. I will discuss the solution now. So as you can see, the signals which are present are A, B, C and D. There are no other signals. So in min term and max term representation, all the signals should be present. Like if you see this particular term, the signals C and D are missing. And here in ACD term, the signal B is missing. So what we can do? So what we can do is that we can add this signal. As you know, if there is a signal B and if we add with its complement, it is basically 1. Like if this everything represents 1, so B plus B bar has to be 1. Okay. So whether we write ACD or we write A B plus B bar CD, it's basically the same thing. Now we will add the missing terms using this way. Okay. So here AB we can add C as C plus C bar and D as D plus D bar. Similarly, ACD can be written as A B plus B bar CD, and the new expression that we have written is same as AB plus ACD. Fine. So we can simplify this. Now we have a repetition. These two signals are the same. If we have two signals, and if we add it, they are basically the same. For example, if you add two zeros, it will still be 0. If you add two 1, if you add two 1 by logic, it will still be 1. Okay. So since we have these two terms as same, we can replace them by one term. Okay. So it will be, and I think that is option B. Okay. Is this clear to everyone? Okay. We will move to the next question. So I will give you about 5 minutes to solve. Okay, I will solve the question in 2 minutes and we will see. Yes, there is a bias for this. For all the floating point model, there is a bias. I can give you a hint that for FP single precision, the bias was 127. Here, the bias is, this is the bias. So are you able to do it? The expected answer is C. I think the free screen has frozen. I think there was some internet problem. I will present my screen again. So I will discuss the solution now. So first we will convert this number to 14-bit FP. Okay. So in 14-bit FP, you have first bit as sign, then you have 5-bit as exponent with bias 16, and then you have mantissa. Okay. It is little different from single precision. I will show you how. So in single precision, this is your mantissa, this is your exponent, and what you will do is that you will take 3 plus you will add 127 bias. Okay. So 130 will be the exponent you will be using in your representation. Okay. In floating point, in 14-bit, you do like this: 0.1100 into 2 power 4. Okay. So
Your mic is muted.
oh, okay, sorry, I did not know. So I will repeat again. Yeah. So according to the question, we will convert these two numbers into 14-bit float, and then and then we will perform the addition. So in the 14-bit float point, your 1 bit is assigned to sign, and 5 bits for exponent, and rest rest 8 bit for mantissa. So it is slightly different from single precision floating point, as you have this number as suppose 12. You convert it into binary. So this is your binary expression. Now you will write as this. Okay. So the difference is that the position towards the left of the decimal should always be 1. Okay, in case of single precision. But in case of 14-bit float point, the bit towards the left of this decimal point needs to be 0. According to the 14-bit floating point representation, the most significant bit in the mantissa should always be 1. Okay. So this place should always be 1, and this place should always be 0. Okay. So this is the representation. Uh, is the difference clear? In single precision, the digit just after, just towards the left of the decimal should be 1, followed by all zeros. Okay. So now this is your exponent. 4 is your exponent. This part is your mantissa, and the bias is 16. So you add exponent to bias, which is 4 plus 16 equal to 20. So this will be included in your 8-bit exponent representation. So it will look like this. So is the conversion clear? Like everybody understood? I will also show you. Uh, okay, so this fine. So this is the representation. Now there is this concept like if you have to if you have to add two float points, exponent should be same. So why this is the reason I can show you. For example, if I have number 112, okay, and I am representing it as 1.12 into 10 square. Another number I have 1046, so I can represent as 1.046 into 10 power 3. So I cannot perform addition because the exponents are different, right? So some way or other I have to make the exponents the same. So what I can do is that I can shift it like this. This way you can see that the exponents are the same. Now I can perform addition. So this is so this you have to keep in mind. So here in this case, as you can see that 1.25 is the smaller one. So we can shift the exponent. For example, expected exponent 10100. Okay. So for for every shift that I perform in Mantissa, I can add plus 1 to exponent. Okay. Is this clear?
So please repeat this step.
Yes. If you look here, the number was earlier 1.12 into 10 power square. Okay. So if I have to shift the number towards the right of decimal. Okay. So if I shift by one place, I will add, which implies I will add plus 1 to exponent.
Right.
Okay. If I shift by one place left, minus 1 to exponent. Okay. So in that way, our expected exponent is this, because that is the exponent for our this number. So the difference is exponent is equal to 3. Okay. So we need to shift the mantissa 3 places towards the right. So it will look like something like this. You shifted 3 places towards the right, and now you added plus 3. We followed this one. Is this clear? So I hope this is clear. Now we have another number 12, which is, so the answer is C. Is the process clear to everyone? How we perform the addition?
Can you repeat the shift in exponent?
Okay. I will explain you using the decimal systems. The same is happening in the this floating point. Suppose I have two numbers. I can write them in this way. Okay. In decimal also, if I have some number such as another number, so we are representing it in this format, in the power of 2. Okay. Are you getting the similarity between these two? So when we have a binary number, we are converting it into floating point by representing it in this way, where we have the power of 2 and the mantissa and the mantissa here. So if we are told to add these two numbers, so in this representation it is difficult. Okay, as you can see, in the decimal equivalent, you cannot add these two numbers because they have different exponents. For example, if you have 123 plus 234, okay, so you can add them because 1.23 into 10 square, 2.34 into 10 square, they have the same exponents, right? So when you add them, 3.57 into 10 square, okay, and this is same as 357, okay, but in this case you cannot add them. So in order to make them of the same exponent size, we can perform shift operation. Suppose 4.32 into 10 square. If I want to increase this exponent from 2 to 3, so what I can do is that I can multiply the number by 10 and divide the number by 10, okay, so which is 4.32 by 10 into 10 power 3. I do it again, it will be 4.32 by 100 into 10 power 4. This is same as this expression, okay, so I can write as 0.0432 into 10 power 4. Now I have this 1 point, let me write it down, 1.2345 into 10 power 4. Here I have 0.0432 into 10 power 4. So it is not possible for me to add these two numbers, okay, 1.2777 into 10 power 4, okay. So whenever we are performing the shift operation, we are basically dividing by 2 and multiplying by 2, okay, like here we have divided by 2 and multiplied by 2, sorry, divided by 10 and multiplied by 10. So this 10 is contributing towards the exponent and this 10 is performing the shift operation in the number. So in this case, what we are doing is that 1.01 into 2 power 3 into 2 by 2. So this will be 1.01 into 2 power minus 1 into 2 power 4, okay. So when we divide 1.01 by 2, this is actually binary. If we divide 1.01 in binary by 2, there will be a right shift operation, so it will be 0.101 into 2 power 4, okay. So now we will perform the same thing again, multiplication by 2 and division by 2, and this multiplied 2 will contribute to the exponent and this will perform the right shift, plus 1 in the exponent. So the equivalent will be 0.0101 into 2 power 5, and now since they have the same exponent size, you can add them. So 1.01011 into 2 power 5 plus 0.01010 into 2 power 5. So this is your final output. So did you understand how right shift is happening? Okay. So moving on to the next question. So I will give you 5 minutes to solve. Yes, actually this is POS form. Okay. So I will discuss the solution now. So I think I will give you a quick recap of min terms and max terms. For example, if I have three signal variables, a, suppose x, y, and z, fine. So I can have different combinations of x, y, z. Like this can be x or x bar, y or y bar, z or z bar, fine. So the range of min terms can be from x, y, z, x bar, y, z, x, y bar, z, all the way to x bar, y bar, z bar. Okay. So whenever this is x, we represent this position as 1. Whenever it is x bar, we will represent as 0. It is very important that if we have decided the order, that if it is x, y, z, if I mention a number as 110, so it is understood that it is x, y, z bar. Okay. If it is x, it will be 1. If it is x bar, it will be 0. And I have the order predefined. Like x is in the first place, y is in the middle, and z in the last place. So if I represent a min term by 110, it represents x, y, z bar. I think it's clear. If I represent the min term as 111, it is x, y, z. If it is 000, it is x bar, y bar, and z bar. Okay. So if we have numbers as xyz plus x bar yz plus x y bar z bar, fine. So we can write the min term denotions as 000. Actually it is 111, 100, and 011. So this is equivalent to 7, this is equivalent to 3, this is equivalent to 4, fine. So the min term representation is 3, 3, 4, 7, fine. So whenever, suppose if I write 1, 4, 6, and I want to know how will the expression look like. So this will be 0, 0, 1. This is for 1. For 4, it will be 1, 0, 0. And for 6, it will be 1, 1, 0. And now, when it is 1, it will be that variable. If it is 0, it will be the complement of that variable. So it will be x bar, y bar, z, x, y bar, z bar, and x, y, z bar. So this expression is equivalent to this. Now the catch is that if we want an equivalent expression in max term, it will be all the digits which are missing. For example, here 0 is missing, so 0, 1 is there, 2, 3, 4 is there, so 5, 6 is there, 7. So this will be the equivalent max term representation. The reason I'm explaining all of this, you will see, because this will be useful in the solution. So we have 5 different terms. So 0, 0, 0, 0, 1, 0, and 011, 101 and 111. So this was your sum of product expression, and if you want an equivalent product of sum expression, so this is your POS. Okay, this is your SOP, and these two are equivalent. Fine. So it will go something like this. So in max term representation, when it is 0, you will have x, and when it is 1, you will have x bar, and the numbers will be added instead of multiplied. So the expression will be like this. So given if you have been given this uh, sum of product, so the equivalent product of sum will be this. Is this conversion clear? If you have three variables x, y, z, so the total number of possible combinations will be from 0, 0, 0 to 1, 1, 1, and the equivalent decimal range will be 0 to 7. So if we have M146, so then remaining digits are 0, 2, 3, 5 and 7. So they constitute your max term representation. Okay, so we will be using this to find out the solution. If you have any doubts, let me know. So the question said a plus b, a plus c. So what we can do is that we can find out the equivalent sum of products, which will be a plus, for example, in BC, the term A was missing, so we added in this way, as I explained in the previous question. Similarly, B was missing, so I have added B. In this case, B and C both were missing, so I have added like this. So it will come down to okay, which is 111, 110, 101, 100, and 011. This is 7, 6, 5, 4, 3. Now, so A plus B into A plus C is basically 3, 4, 5, 6, 7, and we want sum of product expression, which is capital M, and and in product of sum, here you will write the remaining digits, which are 0, 1, 2. Fine. So this will be 0, 0, 0 for 0, for 1 it is 0, 0, 1, for 2 it is 0, 1, 0. For 0 you will write as A plus B plus C. It will be A plus B plus C bar, and this is A plus B bar plus C. So your answer is A plus B plus C. So this is your answer. Okay, B is the answer. Is this clear to everyone? Like, do you have any doubts? So I will move on to the next question. So I will give you 5 minutes for this. I think I will discuss the solution now.
So you are muted.
Sorry, what? Actually, I was not saying anything.
Okay.
So here I have, so the first bit is sine, then we have the exponent part for 8 bits, and then we have mantissa part. So the exponent part has a bias. Okay, so right now it shows 129, bias is 127. So 129 minus 127, this is your actual exponent. Now we have this mantissa, so it looks something like 1.01000 and multiplied by 2 power square. Okay, so which is equal to 101. This is 5, and we have sine equal to 1, therefore it is negative. So answer is -5, option C. Okay, so next question. I think I will discuss the solution now. This is fairly a very simple question. So the sign bit is 0, which means that it is a positive number. Then we have this part as exponent. So 0, 1, 1, 1, 1, 1, 0, 0. This is equal to now uh, we have to subtract bias to get the exponent. So this is exponent that we obtained. This is the bias that we subtracted from this. Now let's look at the mantissa part. So it is 1.1101101, this is equal to mm, 1.8515625. Okay, so our number is 1.8515625 into 2 power minus 3, which is equal to 0.231445 or 2.31 into 10 power minus 1. So the answer is C. Fine. Everybody got the answer, or do you have any doubts? I think uh, the part of the question where everybody might make mistake is the exponent part. Okay. because I think people generally make mistake in adding or subtracting the correct bias. Otherwise, everything is fairly simple. So we will move on to the next question. So I basically underlined them so that it will be easier for you to copy down the options because the number of bits are large. Okay. So your question is that how to find out where to add or subtract the bias value. So bias is always subtracted. Fine. The bias in the bias single precision in single precision, that is 32 bit, is 127, and this is always subtracted to get the decimal value. And okay, let's make it simple. You have some number, you have some binary number such as 1011, something like that. You will convert it into 1.011 into 2 power 3. Okay, so if you are converting in single precision, you will always have to add to this exponent, you will have to add a bias of 127. Okay, so that you can write the single precision format. Fine. If you have the single precision format, from the exponent you have to subtract 127 to get the original exponent, which is this value. Okay. In case of uh, 14 bit, in case of 14 bit floating point model, the format is like this. Like if your number is this 1011, you will convert it into 0.1011 into 2 power 4 and to this exponent 4 you will add bias of 16, okay, to get your exponent in the 14-bit format. Fine. And when you are converting from 14-bit float point to the decimal value, then you will subtract 16. Things are different in both the cases. For example, 16 is 1 followed by 3 zeros, 4 zeros actually. But in case of 127, this is basically a string of all ones. So there is somewhat difference. You might expect that in this case, why 127? We should add 128 because that is a perfect power of 2. But I do not have the answer for that. It is basically how they follow the format. It is also expected that here also you should add 15, but they add 16. The format is to add 16. So I will give 2 more minutes and then I will discuss the solution. Uh, I will discuss the solution now. So first you will convert the number to simple binary format, which will be 1 followed by 5 zeros. Okay, we can write this as 1 into 10 power 1 into 2 power 5, but we do not need this expression because this expression will be used in single precision. So there you have so there 5 will be the exponent, and now what we need is that 0.1 into 2 power 6. So this we will use for 14-bit FP. Okay, so in this case 6 is the exponent. This part will be the mantissa. So this will go like this: 6 plus bias which is 22 equal to So this is your exponent part. Okay, your mantissa part will be 1 0 0 0 0 0 0 0. So, and this number is positive, so we have the final answer as 0 1 0 1 1 0 1. Okay. Hmm. I think we have got a situation over here where our answer does not match with any of the options. So the options are actually wrong. Okay. If you see, I think this one is pretty close to your answer. Only had this bit been 1, it would have been the right answer. So you are saying that we don't have to add bias. Why is that the case? I think in 14-bit precision we add bias. Okay. So the situation is that these two are probably these two are different representation. One representation is simplified 14-bit float point. Another is revised 14-bit float point. So in the case of revised, you have to add bias of 16, and I am assuming that in this case no bias has to be added. In the question, it has been mentioned simplified 14-bit float point. So in that case, option A is correct. Fine. So we will do one last question. Uh, I hope this is clear to everyone. Uh, does anyone have any doubts? So these two representation are different, simplified 14-bit and a revised 14-bit. I will move on to the next question then. Fine. Uh, this is a very simple question. I think I have discussed a similar question before, so it won't take much time. I will give you 2 minutes to think. So as I mentioned earlier, that if I have 4 signal or 4 variables, the possible combinations will be from 0, 0, 0, 4 zeros to 4 1s, which is from 0 to 15, right? And in this case, in this case, the right answer is the option with the missing numbers. So it will be 3, 7, 11, 12, 13, 14, and 15, which is option A. I hope everybody got this answer. So I will discuss one more question, and that will be the last question. I will discuss the solution in 2 minutes. So this is D, and rest of them are zeros. Okay. I think I should discuss the solution now. Do you want more time? So C can be represented as 1. C is basically 12, D is 13. This is sign bit. This is exponent, and this is mantissa. So mantissa is 1.101. Okay. So our number is 1.101 into 2 power 4. This is 11010, which is 26. Okay. And we have sign as 1, which means negative number. So the answer is minus 26. Option C. Okay. Um, so that's all for today's tutorial.